Section 5.4, Integration Formulas and the Net Change Theorem. In this section, we're going to discuss one of the applications of definite integrals, which is to calculate the net change of a function. Thanks to the second fundamental theorem of calculus, we have that the new value of a changing quantity equals the initial value plus the integral of the rate of change. In other words, f of b equals f of a plus the integral from a to b of f prime of x dx, or the integral from a to b of f prime of x dx is equal to f of b minus f of a. The second formula is a direct result of the second fundamental theorem of calculus. The antiderivative of f prime is f itself. The quantity here, f of b minus f of a, that would be the net change of our quantity. So what this result tells us is when we integrate the rate of change of a function over an interval, that is equal to the net change of that function over that interval. So as an example, suppose the marginal revenue of a company since 2010 is given by f of t equals 4t squared plus 3t, thousands of dollars per year, where t is the number of years since 2010. First, we want to determine, as time increases, is the revenue always increasing? To answer this question, we have to recall what marginal revenue represents. Marginal revenue is the derivative of a revenue function. So what we're saying by the wording of this problem is the derivative of our revenue function is equal to f of t, which is 4t squared plus 3t. How do we determine from the derivative that the revenue is always increasing? Well, recall that in general, a function is increasing when its derivative is positive. So we want to see if 4t squared plus 3t is always increasing. To help, we'll set our derivative equal to 0, which is our f of t. We were already given the derivative, so there's no differentiation that needs to be done. Factor, and we get t times 4t plus 3 equals 0, which means t is 0 or negative 3/4. Since we are only modeling the marginal revenue since 2010, we can ignore the negative 3/4. Making our sign chart for f of t, which is r prime of t, we only care about values that are 0 or larger. If we take a value bigger than 0, plug it into our f of t, we get a positive value. So from here, we can conclude f of t is greater than 0 when t is greater than 0, so the revenue is always increasing. Now we're going to determine what is the revenue between 2012 and 2020. We have to be very careful with the wording of the problem. Our model represents the marginal revenue for the company since 2010. Since it is the marginal revenue since 2010, we first have to change our years 2012 and 2020 into appropriate values for t. 2012 is 2 years after 2010, so t would be 2 for 2012, and 2020 is 10 years since 2010, so we'll have t equals 10. Because we just want to know the revenue between 2020 and 2012, our goal is to figure out r of 10 minus r of 2. The problem is we don't have a revenue function, but we do have a marginal revenue function, which represents the rate of change of revenue. Since our marginal revenue is 4t squared plus 3t, then r of 10 minus r of 2 is going to be equal to the integral from 2 to 10 of 4t squared plus 3t dt, which we can now evaluate using the fundamental theorem. The antiderivative of 4t squared plus 3t is 4/3 t cubed plus 3/2 t squared. Now we can plug in our bounds and then evaluate, and we get 1,466.67. As for the units, our marginal revenue is in thousands of dollars per year. Recall that the derivative is the units of our function divided by the units of its independent variable. Since time is measured in years, then our integral would have the same units as our function, which would be here is thousands of dollars. Oftentimes, in many different applications, we may use different words that all represent net change. When it comes to position, velocity, and acceleration of a particle on a line, recall that we use v of t to note the velocity of a particle. When v of t is positive, then the particle is traveling in what we're going to call the positive direction. While if v of t is negative, the particle is traveling in the negative direction. So keep in mind, since our particle is moving along a line, it can either move one of two directions. One of those directions we call positive, the other we call negative. As for the net change of the particle's position, we're going to call that net displacement or displacement. So the net displacement of a particle from t equals a to t equals b is the net change of the particle's position. And since velocity is the derivative of position, the displacement of a particle can be calculated by finding the definite integral from a to b of v of t. One thing to keep in mind is net displacement only considers where the particle stops and starts. So if we look at the number line below, suppose that the points represent where a particle is located on this number line for various values of time. So for t equals 0, the particle starts at position 0. At t equals 1, the particle is at position 10. While t equals 2, the particle is at position 5. The displacement only concerns itself with the distance between the start and the stop position. So here the displacement would be the final position 5 minus the starting position 0, which is 5. Keep in mind displacement can be positive or negative. If it is positive, that indicates that the particle moved forward. If it is negative, that means the particle moved backwards. Keep in mind that a particle can change direction many times over a time interval. For example, here on our number line, from t equals 0 to t equals 1, our particle moved forward 10 units. but from 10 equals 1 to 10 equals 2, it moved backwards. When we want to account for every step that this particle took, we are looking at the total distance. Now, the total distance traveled by a particle from t equals a to t equals b is the integral from a to b of the absolute value of v of t. And recall that the absolute value of v of t is the speed of the particle. So looking at this number line here, the total distance traveled would be equal to, well, first, the distance traveled from 0 to 10, which is 10 units, plus the distance traveled when going from 1 to 2 units, which is 5 units. Even though it's going backwards for total distance, we are ignoring direction. So the total distance traveled is 15 units. The biggest difference between net displacement and total distance is that net displacement is only concerned with where we start and where we stop. All the times in the middle are irrelevant. Total distance traveled ignores direction. It doesn't matter whether we moved forward or backwards or switch directions in between. We account for every step taken throughout the motion. Suppose a particle is moving in a straight line. At t seconds, its velocity in meters per second is v of t equals t squared minus 3t plus 2. First, we're going to find the displacement of the particle over the interval 0 to 2. Since we're trying to find the displacement of our particle over the interval 0 to 2, we can do this by finding the integral from 0 to 2 of v of t dt. So our v of t is given to be t squared minus 3t plus 2. Using the fundamental theorem, we'll find the antiderivative, which is t cubed over 3 minus 3t squared over 2 plus 2t. And we'll evaluate it at our bounds, which are 2 to 0. When we plug in our bounds and simplify, we get 2/3. As for the units, since velocity is in meters per second, then our position would be measured in meters. So our displacement would also be measured in meters. What this means is that at t equals 2, we are 2/3 of a meter away from our starting position. That does not mean we traveled a total distance of 2/3. It just means when we only look at the start and the end, we only traveled 2/3 away from the starting position. Next, we're going to find the total distance traveled by the particle over the time interval 0 to 2. So here, we're going to evaluate our integral from 0 to 2 of the absolute value of velocity. Since we know what v of t is, that means we're trying to evaluate the integral from 0 to 2 of the absolute value of t squared minus 3t plus 2. Absolute values are a little tricky when it comes to integration. The strategy is to try to break up our integral so that way we can evaluate the absolute values. We know that the absolute value of a positive value is itself, while the negative value is the opposite. So what we're going to do is we're going to focus on determining where our t squared minus 3t plus 2 is positive or negative. To help us, we're going to make a sign chart of the t squared minus 3t plus 2. We're going to start off by setting the t squared minus 3t plus 2 equal to 0, and we're going to solve for t, and we get that t equals 2 or 1. These two numbers are going to serve as partition numbers for our sign chart for the t squared minus 3t plus 2. As for my sign chart, since my integral's from 0 to 2, I'm only going to consider the number line between 0 and 2. Now I'm going to place my partition numbers. T equals 2 is already the endpoint of my interval, while t equals 1 will be right in between. And just like with all of our sign charts, we'll take sample numbers, plug it into the function we're trying to make the sign chart for, and fill out the sign. If we pick a value between 0 and 1, like 0.5, and plug it into our t squared minus 3t plus 2, we get a negative value. But if we pick a value between 1 and 2, plug it into our t squared minus 3t plus 2, we get something positive. So what this tells us is our t squared minus 3t plus 2 is negative on the interval 0 to 1, but positive on the interval 1 to 2. So with this information, we're going to rewrite and separate our integral, where one integral will be the integral from 0 to 1, while the other integral will be from 1 to 2. Now, because we know that t squared minus 3t plus 2 is either positive or negative in the respective integrals, we can evaluate each absolute value. For the 0 to 1, t squared minus 3t plus 2 is negative, so its absolute value will be the negative of the quantity t squared minus 3t plus 2. While from the interval 1 to 2, we know that t squared minus 3t plus 2 is positive. The absolute value of a positive number is itself. So we can drop the absolute values in the second integral. Now we can find the antiderivative of both integrals, then plug in our bounds and subtract, and we get that the total distance traveled is 1. As for the units, it would be meters, just like the displacement. In general, total distance will be either greater than or equal to displacement. This is because total distance accounts for every step taken without paying attention to the direction traveled, whereas displacement only is concerned with where we start and where we finish, and accounts for the direction traveled. In the next example, we're given that the acceleration of an object in meters per second squared is given by a of t equals 2 cosine of t. The initial velocity of the object is v of 0 equals negative 1. We want to find an equation v of t of the object's velocity. Recall from our previous units that velocity is the derivative of the position function, and that acceleration is the derivative of velocity. Because we know acceleration is the derivative of velocity, this tells us that velocity is an antiderivative of acceleration. So our velocity is an antiderivative of 2 cosine of t, which means our velocity function is equal to 2 sine of t plus c for some c. The 2 sine of t plus c is the general form of the antiderivative of 2 cosine of t. However, a particle can only have one velocity at any given moment. So we don't want every antiderivative. We just want one specific antiderivative of our acceleration to use as our velocity function. But how do I determine the value of c to get the correct velocity function? We're given that the velocity of our particle at t equals 0 is negative 1, because we're told v of 0 equals negative 1. If we use this fact, we can take 0 and plug it into our general form of our antiderivative, and we get 2 sine of 0 plus c should equal -1. Fortunately for us, sine 0 is 0. Anything times 0 is 0. 0 plus c would be c, so we get c equals -1. Now that we've figured out the specific value of c we need, then our velocity function is v of t equals 2 sine of t minus 1. Next, we're going to find the object's displacement in meters between the time of 0 seconds and 3 seconds. Recall that the object's displacement will be the integral over our time interval, which here is the interval 0 to 3 of velocity. In the last step, we figured out what our velocity function was, so our displacement will be the integral from 0 to 3 of 2 sine t minus 1. Now we'll use our fundamental theorem, and we get that the antiderivative of 2 sine t minus 1 is -2 cosine t minus t. Plug in our bounds and subtract the results, and rounding to 4 decimal points, we get 0.8323 meters. And our units here will be meters. Because our acceleration is in meters per second squared, velocity will be in meters per second, while position or displacement or total distance will all be measured in meters. Now we're going to find the total distance traveled over the interval 0 to 3. Since we're finding total distance, then we are finding the integral from 0 to 3 of the absolute value of our velocity function. And our velocity function, we already know, is 2 sine of t minus 1. Just like in the previous problem, we need to figure out where the 2 sine of t minus 1 is positive or negative, so that way we can split up the interval and rewrite our integrand without the absolute values. We'll start by making a sign chart for our 2 sine of t minus 1, which means we need to see where it's going to be equal to 0. If we add 1 and divide by 2, we get that sine of t equals 1/2. Keep in mind, we only care about the solutions for sine of t equals 1/2 in the interval 0 to 3. Looking at our unit circle, keeping in mind that 3 is just slightly under pi, we get pi over 6 and 5 pi over 6. Pi over 6 is smaller than 1, while 5 pi over 6 is smaller than 3. From there, we can make our sign chart. Because our integral is on the interval 0 to 3, we're only going to be concerned with the values between 0 and 3, and we'll place our partition numbers. If we pick a number between 0 and pi over 6, plug it into our 2 sine of t minus 1, we'll get a negative value. If we pick a value between pi over 6 and 5 pi over 6, plug it into our 2 sine t minus 1, we get a positive value. And if we pick a value between 5 pi over 6 and 3, plug it into our 2 sine t minus 1, we'll get a negative value. So from here, we're going to break up our integral into 3 other integrals. One from 0 to pi over 6, the other one from pi over 6 to 5 pi over 6, and the last one from 5 pi over 6 to 3. As for the integrand, because we know the absolute value of a positive number is itself, the middle integral from pi over 6 to 5 pi over 6, where our 2 sine of t minus 1 is positive, the integrand will be 2 sine of t minus 1, where we can drop the absolute values. As for the other 2 integrals, since our 2 sine of t minus 1 is negative, the absolute value of the negative number is its opposite. So both the first and the last integral will have an integrand of negative of 2 sine of t minus 1. Now we can apply the fundamental theorem, and we get that the total distance traveled is approximately 1.7594, and the units would be meters.